In the past lectures, we have seen how actors collaborate to achieve a common task, but now we will look a bit more in detail on how to compose them. The type of an object describes how that object looks like from the outside, what you can do with it. When looking at an actor, the role of the type is played by the set of messages it accepts. The set of messages is not bound to the name of the actor, and hence the type described by it is not nominal. An actor's type is structural. Since an actor can change its behavior over time, the structure can also change, and that means that the type of the actor could change in terms of a protocol which you exchange with it. If you look at the types appearing in actor implementations, we have seen two main methods. First is sending a message, that's the tell, and it has signature any to unit. And the second is the behavior inside the actor, which is a partial function, again from any to unit. These types do not restrict what you can send. In a sense, you could say that actors are not usefully typed, as represented, for example, in Scala and Akka. But it should be noted that this limitation is not fundamental. While it is true that an actor can change its behavior arbitrarily in principle, most actors you write will not do that. They will either always accept the same set of messages, at least the types, or it might change, but then the total set of all messages ever accepted will be bounded. In all actors we have seen so far, we defined the complete set of messages they accept in their companion object, for example. This makes it possible to statically verify that when you send a message to an actor, it could in principle at some point have a chance to handle it. Means you could reject a large number of errors. This is tried out. There is an experimental implementation of typed channels. In Haskell, there's Cloud Haskell with typed channels between actors as well. I think we will see some development in that area. However, the type system will never allow us to express which state an actor currently is in. So we can deal with the complete set of messages, but we cannot statically determine whether an actor will process a given message, for example. There are many reasons for that. One of them is that delivery is not guaranteed, for example. Another one is that actors may interact with several different parties, and if we have here, for example, Alice and Bob both talking to Charlie, then Bob may send a message changing the state so that when Alice sends a message, that might find Charlie in a state which is not suitable for that message anymore. And since this can happen concurrently, it is not known statically at compile time, so the compiler will not be able to catch those kind of mistakes. However, having fully typed actors is something which we do not have yet, so let us use what we have right now. Given that sending a message to an actor does not return anything, and the types currently are not really restricted, it is obvious that actors cannot be composed like functions. Instead, we have seen that actors collaborate. Like human organizations, you can split down a task into subtasks and have each actor perform its own part, and then the results are taken together. They are composed and replied to the client which asked for the operation to be performed. This means that actors are not composed like functions. They are composed at the protocol level. This gives the actor the possibility to do everything you can think of conceptually using function composition. So you can translate the values passed into a function, you can translate its return value, and the same thing you can do with messages flying back and forth. You can also call multiple actors and then aggregate the results. But what protocol composition can do, which function composition cannot do, is, for example, to alter the frequency with which an actor is called, or the precise timing of the calls, or perhaps dropping messages injecting new messages. There is a lot more freedom here, but this freedom is bought by less type safety. Let us now look at a few patterns of what you can do. The most fundamental pattern is one which we have seen since 2 weeks ago, reappearing everywhere, and that is the request-reply pattern. It is so common that in akka the sender reference is kept exactly for that purpose, because you so often need to reply, and for that you need to know to whom to reply. Let us say that Alice wants to know something of Bob and sends a message. Together with the sender information, this enables Bob to reply. But we have seen other uses. For example, Bob could forward the message to Charlie, for example. So it's basically this. And forwarding means that the sender reference stays the same. So the sender of that message here will not be Bob. It will be Alice. And then the reply from Charlie goes directly back to Alice. This means the fact that simply putting the sender reference in the message and letting it travel with it allows dynamic composition of actors. Bob can decide dynamically whom shall handle the request, and then the reply will go back to the one requesting it. We could also take an actor ref and wrap it inside another actor, say here this audit trail, which does nothing but forward all messages to the target, like so, but it logs every message which it has forwarded to leave this audit trail. These interceptors are trivial to make, precisely because messages are not typed specifically. We can just pass along anything that might be sent. Another useful pattern is the one where you expect exactly one reply. We call this the ask pattern. You ask a question, you get one reply. This is also pretty common, which is why it is implemented as a pattern within akka. Importing this gives you an implicit conversion on actor refs, which gives it this question mark operator here. We pronounce this user service ask find by email in this case. The actor which we are looking at here might be a part of a blog management system, and it has a reference to the user service, and you can ask this posts by email actor to find all the posts which have been posted from a certain email address. Unfortunately, the user service does not offer this kind of information directly, so we write a little actor which transforms what the user service can give us. So when we get a request with an email in it, we ask find by email everything you know about that user, and this returns a future. Since actors are not usefully typed, as we've seen, this is a future of any. But we expect back actually a user info. There is an operation map2 which takes a type, and that will under the hood transform the future, doing a checked cast. So after this we have a future of user info. Then we can map that and take this info and look at it. For example, it might have a list of posts which we filter, whether the email matches, and this filtered list then goes into the result. So this has been transformed into a future of result now. And then in the end, we pipe it back to the sender. We have seen that before. The line here takes all errors which might occur and takes them, this is throwable, this is an exception, and wraps them in a failure message. Let's say failure was also a message defined by posts by email. And this is done such that pipe2 always sends a normal message, so either a result or a failure back to the sender. Which are the pieces which can go wrong here? We have this ask operation. We have seen that actors only can send messages to actor refs, and there is not really an explicit actor ref to reply to in this case. What the ask operator does is it creates a little, very small, tiny, lightweight pseudo actor, which just is an actor ref linked to a promise. This actor, of course, has a name and everything. It needs to be registered, so it also needs to be garbage collected when it is no longer needed. Unfortunately, that is not very easy to determine because actors are also location transparent. So, for example, user service might be on a remote system, and we do not know when or if it will reply. For this reason, the ask operation takes an implicit timeout, which we have set to 3 seconds here. After these 3 seconds, the future will be completed with an ask timeout exception, and this little pseudo actor will be stopped. So this is the first thing which could go wrong. We could see an ask timeout exception here. Map2 does a checked cast. So if the reply was not of type user info, then we will find a class cast exception in this future. So it will be propagated here. And then finally, within the map, whatever goes wrong here would also end up in the recover case. You will find this sequence of steps quite common when transforming another actor in this kind of facade fashion. An alternative to this pattern would be to spawn an actor, of course. So when we get an email, we could create a little customer actor which uses tell to communicate with the user service, and then the user service sends back, and this actor would then reply to the original sender. The ask operation here is just an optimized form of this. The actor which is created in this case consumes less resources than a real actor would. Even though a real actor is really cheap, but if you do this 1,000,000 times per second, then the difference matters. Another consideration is that this code is fairly clear. We ask this of some other actor, then we make sure it has the right type, we transform it, catch errors, and pipe it back. So if it is this kind of easy transformation, then ask is fine. If you find yourself writing very complicated expressions in here, or multiple steps with different futures, and the error recovery paths get ever more convoluted, then it is for sure time to switch to a customer actor. The third possibility is to keep track of who the original sender was by including this information in the message which travels to the user service and back. If you are designing your own system from scratch, that might be the most efficient way to do it. But if you need to work with a user service in this case, which you cannot modify, then you need to use ask or a customer actor. Another use case where the ask pattern comes in handy is if you need to aggregate results from multiple other actors. So let's say this is a blog post summary actor. And when it gets a request for a certain post ID with user and password, then we generate 3 requests. First, we ask for the status of the post, some publisher actor. This result will be some kind of post status. Then we retrieve the text from the post store by issuing a GET request. But then we also ask the authentication service whether this user and password is a valid combination and whether that user is authorized to see this kind of information. We use a for comprehension to tie these 3 futures together. And when all of them are successful, this code will run. So we check whether the authentication was successful. In that case, we send back the result. Otherwise, it gives a failure, saying not authorized. This is a transformed future. We started out with a future here, and then this is translated to flat map and map of futures, and this yields a future. We have a response here, which is a future of result or failure, and this response is then piped back to the sender eventually. This is an extremely common pattern if you are running like a web store or some big website and the user requests, for example, his own homepage on some social network, for example. There will be possibly hundreds of such requests involved in answering this one GET operation from the client's web browser. But an actor is not limited to transforming the values which travel. It also can transform, for example, the lifecycle monitoring or the semantics of how an actor works. For example, let's say we have a file worker here, which is an actor which can write things to files. Let's say we have a request here to write something. The file worker will try to do that, but we know that during I/O many things can go wrong. So this write might just fail. Then, of course, there will be an exception and the supervisor will handle it. But even though the file worker might be restarted, for example, there will be no reply to this request because the processing failed. And the only way for the client to determine that it was not successful is to wait for a timeout to happen. That can take a lot of time because you need to foresee I/O operations could take some seconds, and then a reasonable timeout window would be impractically long. What we can do is to wrap this file worker's function in another actor. Let's call it file writer. And then the write does not go here anymore. It is sent here. The file writer will create a worker and supervise it and monitor it. And then, well, successful results could come back, or it might fail, or terminate before sending a successful result. No matter what, the file writer itself did not perform the risky part, so it is a lot less likely to fail. Therefore, the writer very likely can respond, done or failed, making the interaction with this file worker more safe. Here I have sketched this out a bit in code. We have the file writer, and when it gets a write command, it will create a new file worker for the file and tell it to respond to self, so to the file writer. Then we watch it, and we also need to keep track of for whom this particular worker is performing the work, so we can send back the done or failed messages. Then, if anything goes wrong, we have a stopping strategy. That means that the worker will not be restarted, and in the end we either get a done message or the actor terminates. Whichever happens first will be successful because we look into the map for the sender. This is now the worker actor, and if there is still contents in the map, then we send the done message and remove this one. This means that when it terminates later, this will not find anything anymore. But if it terminates without having sent a done message, we send a failed to the client. Using ephemeral actors which are created per request is a quite common pattern, especially if the work to be performed is risky. We have seen a few patterns of how you can compose actors to translate values going in and out or to validate requests. But it is easy to imagine many more of these, for example, rate limitations or also access control. These are things which, with normal method calls, are hard to implement. Or, for example, access control needs to use aspect-oriented programming, for example, to insert it around method calls. Since actors are purely based on asynchronous message passing, we have many more possibilities on how to compose them on a protocol level to achieve these things, for example, without using aspect-oriented programming. On the other hand, this great flexibility is part of the reason why actors are not as usefully typed or as strictly typed as method calls.